Good morning all. So first of all, this is going to be a very, very low-tech talk. Saturday afternoon as I was coming home, I left my backpack on a train. It's now tagged as 3063 at the San Carlos Samtrans headquarters. So over lunch, I'll be going to get it. And the result is I'll be delivering this particular talk in a very, very low-tech way. It's a handful of notes. You should count yourselves very lucky. My 14-year-old daughter, upon noticing my discomfort, said, "Daddy, you need to deliver the entire talk as interpretive dance." I will not dance as the bear has danced before. Again, my name is Paul Brown. I'm, for my many sins, the chief scientist now at Paradigm 4, where I work on a platform called XLDB. It's a database. Databases do really boring demos. I'm not going to do a demo. If you want a XLDB demo, contact Douglas Slaughter from the NIH. He's here, and have a look at the Genomes project. XLDB is the database behind that. Sound like a Looney Tunes thing. What instead I'm going to do is, as you can probably tell, I lost my hair in the last great database war of the 90s. And I have a few sort of thoughts about what we're learning at XLDB and Paradigm 4 about our product moving ahead, the experiences that we're having. That's the last time I'll make a commercial plug. So the title of this talk is Lessons from Your Daddy's Database Wars. I'll take two lessons. The first one is about necessity. It's about what the platform must have. That's to say, there are lessons about what we learned from, as Oliver points out, data warehousing that we have to roll forward into the next great world of big data. And I don't think in some quarters those lessons have been really absorbed by the community. The second thing I'll talk about is sufficiency. If you look at the nature of big data, and to my mind, big data is Internet of Things. Essentially, if you've got any human in the loop, swiping a card, clicking a mouse, selecting a drop-down, there's a human in the loop. Humans have a limited bandwidth capacity. We can only swipe cards so many times. We can click so many times. It doesn't matter how much you pressure human beings to type stuff in, you're never going to get more than a certain upper limit of data. By contrast, the Internet of Things is about a vast connected cloud of sensors, generating data constantly, measuring the environment around it. That data, I will argue, is sufficiently different in kind as to make it different in type. And if we are going to solve the challenge of the big data movement ahead, we're going to have to change some of the tools. The tools we have today are not sufficient. What will be sufficient? So I'll talk about those two things. First thing. It's important to reflect that although Oliver's slides sort of said data warehousing, Teradata was there, IBM DB2 was there, some of the big Hitachi boxes were there. Now we have, Amazon have their own Actian-based products and so forth. In about 1989 through 1993, it wasn't at all clear that data warehousing was going to win. Right? We had alternatives where each enterprise would build a big network-attached file system, the Andrew file system, NFS had become standard. They would export all the data from the operational stores, they'd store it in a big NFS mount point, and they'd let people write their own, God forbid, Perl scripts to take care of it, for those of you who remember Perl. And the idea was that this was a way of getting analytic information quickly and flexibly to end users. No one had to learn to write complicated languages like SQL. They could instead just write Perl scripts. That, of course, did not win. Now, why did that not win? And the reason that is generally given, at least to those of us of the database persuasion, the belt and suspenders brigade, is that there were several failures, not so much of the algorithm complexity, but of the quality of service guarantees you can get from a file system and a scripted language. I'll talk about three. The first one is data quality. You might have heard, and I'm now going to pass an opinion that I hold with about 0.8 probability. You might have heard a bunch of people from the NoSQL community saying, schema doesn't matter, we just make up schema as we go along, we use a triple store to store stuff, we use a document repository like XML where the data values are typed at the query time, not when data is stored. Here is the problem with that. Schema is beautiful. Schema allows you to distinguish that data which is consistent with the rules of the enterprise from that which is garbage. No schema, garbage. The second oldest refrain in computer science is garbage in, garbage out. If you don't have a schema, if you don't have a way of understanding the data models you're reasoning about, the results of your analysis is going to be utter bullshit, and you will find yourself in front of a CEIO wondering what the hell happened when you made that hedge fund bet. Who heard about the London whale? The London whale, who lost, I believe it was $17 billion, was an Excel spreadsheet, a Python extract, and that's how he was doing his trading. That's what happens when you don't have high quality data at your disposal. Second thing, concurrency and sharing. If you've got a file system and you've got people simultaneously adding to that file system and reading from it, the concurrent access becomes a nightmare. flock is a wonderful system call, but it is not a semantic utility. It is a way of blocking control and access to files. If you don't have transactions, if you don't have the ability to have people simultaneously reading and writing data to and from the system, if you don't have the ability for multiple people to share a consistent and isolated view of correct data, again, you're now back in bullshit territory. You're now back in who the hell knows what this analysis means. If you don't have transactions, if you just have file locking, you've got a big problem. And the third thing is productivity. Perl is an awful language. Python is a smidgen better than Perl. They're hard to use, they're scripted languages. You really need a PhD, or not a PhD, but you need a computer science background to know how to use those languages well. SPSS, tools like Tableau, Cognos, the high-end metrics, the high-end tools for visualization and data interaction, they draw you pictures, they give you drop-down menus, they're simple and easy to use. Even at Harvard MBA can use one of those tools, all right? Productivity is important. I can't drive a simple graphical user interface on top of Python, right? It just doesn't work that way. I need to have schema, consistent views of the data, and high-level declarative models for getting at that information. What I don't need is file systems, NoSQL, and scripted languages. Right?
Well, I would consider that a great dance.
Well,
you want to continue?
I will, but I'm surprised.
Oh, my goodness.
I was wondering if you wanted to dance.
Okay, well, let's go.
Now I'm frightened. All right.
Okay,
So
two more minutes.
2 more minutes, very good. Big data. Big data is described in terms of volume, variety, and velocity. All right, but what I'm going to focus on for a moment is the nature of the data that's coming through with great variety, at great volume, and at great velocity. Now, what is the significant difference between all these machines that are out there and the kinds of technology that we've built enterprise warehouses on before? I would argue the difference is measurement. All of what the Internet of Things devices gather are measurements about information. It's the change in the resistivity of a piece of metal as temperature changes. It's the number of photons that hit the cell as the light's coming through. It's how wet the atmosphere is. Your Nest device on your wall is understanding carbon monoxide levels, oxygen levels, temperature, hydraulic, all sorts of good stuff. These are measurements. Human data encodes information. You swipe a barcode, there's a discrete value on that barcode, that's what the computer records. The technologies at high-level languages that we've come up with in SQL are about reasoning, about encoded information. SQL group by is a good example of this. SQL group by is a partitioning operator. I pick up the data and I subset it into mutually exclusive subsets of that data and then run some aggregation on it. Measurement data is observational. It's subject to observational error. It's a random variable. It's a double precision or a floating point number. The only way to reason about it is as sets of observations. It's using things like ANOVA, Fisher test, and so on and so forth. Fourier transforms in the case of time series analysis and so forth. None of these building blocks to the analysis of measurement data currently exist in languages like SQL. It's not sufficient. To get sufficiency, we're going to be looking at languages that look more like high-level R, that look more like what MATLAB supports. So very quickly to summarize, necessity, if you don't got transactions, you don't got quality of service in your data warehouse and your decision support system, you've got bullshit results. Garbage in, garbage out. Sufficiency, the internet changed everything. The Internet of Things is going to change everything again. We're shifting from a world of encoded information to measured information. The tools that you work with on that data are going to have to understand random variables. They're going to have to understand real numbers.